We're going to take a look here at trends in the acidity of carbonyl compounds. So let's take a look first. Esters are generally less acidic than ketones. Let's see if we can figure out why that is. So down here below, here's our ketone. So here is our alpha position that we're going to be deprotonating here. pK of those are somewhere around 20-ish or so. We'll have a base to do our deprotonation. Right down here we form an enolate that has this resonance stabilization. So we're coming around and we're doing this. So that helps, that carbonyl participates in carrying the burden of that negative charge. It helps distribute it in the molecule. Esters, however, are already in resonance. So just by themselves, without doing a deprotonation, they're already involved in this resonance that we see over on this side, right? So here we have our electrons coming around here, plopping up to the top just like so. Okay, so that gives us a pK that's higher, which means that we're less acidic. So deprotonation of that alpha position puts a negative charge here, right? So this has resonance. Of course, we can come around here and we can do this. So that's favorable, right? That would give us our R, CH, double bond, carbonyl, minus charge, and then your OR over here. But remember that this is also in resonance over here with its ester linkage. So the other thing that we get here is our R, right, with our CH minus, essentially. And then we have our carbon, OR, just like so. Plus charge there. Minus charge here. So that extra resonance is actually kind of distracting from helping stabilize the enolate's negative charge. Okay? So if we look down here below, here's the general trend that we have seen in this whole chapter. So you have esters that have pKs about 24. Right, so here's our 24. You come down here and you have ketones. Ketones have pKs of about 20. We just mentioned that. And then the thing that we're going to look at in the next couple lectures here is we're going to look at these dicarbonyls. So dicarbonyls are going to follow that same trend. We're going to look at dicarbonyls and dicarbonyls that have esters. So here's a dicarbonyl alpha position, but an ester linkage over here on one side. So those are going to be more acidic than just looking at our ester up here, because we have two carbonyls, all right? And if we have no ester linkage at all, then we're the most acidic down here below, because there is no competing, right, ester resonance to detract from stabilizing our enolate here. Okay? So what we're going to do is we're going to take these two esters and we're going to react them to form these beta dicarbonyls. Okay? Now, one thing I want to point out to you here is this, is that here this is an R prime O, and the base that we use is an R prime O. So it's important to note here, right, that ester linkage, that we have to make sure that we use an R prime O minus as our base. Now you may wonder why that's the case. Well, one of the problems is here is that when you have an R prime O minus is that you get an esterification reaction. You get something called trans-esterification. So if we have an R prime O minus, the trans-esterification product is the same as the reactant. So it won't really make much of a difference. But if we had, hydroxide in here, then you'd basically make the carboxylate of that. Okay. Now this is a new stereocenter here, and this little wiggly weird line like that is something that we use sometimes in organic chemistry to denote that you get a mixture of wedge and dash products there. Now often when we carry out this reaction, the two esters are typically the same. Right? So let's take a look at the mechanism down here below. It's pretty cool. So let's take a look at the mechanism here. So we're going to start off here with this ester. Let's put a CH3O on here, and then let's just make this an R. And then it'll react with itself here. So we're going to take that and we're going to add a base. Now the base that we add here needs to be CH3O minus, and we'll use methanol as the solvent there. Okay, so the first thing that happens is we're going to come over and we're going to do a deprotonation. That shouldn't be a huge surprise there. So that's going to give us our enolate. Right, and then of course that has resonance there. So what I'm going to do right now is I'm just going to write plus resonance. I'll let you guys draw that out, but there's two other ones, right? All right, now that's going to then react with another molecule of itself now. And we're going to come around here and do this. If we can find the right direction there. And there we have it. Okay. So our main goal next here is to figure out how to draw that product. So things get kind of large for the rest of this chapter. The molecules grow in size. So let's start off here by simply just doing this. Okay. Now this carbon right here is going to make a bond with that carbon right there. So let's draw that. So we're coming up here, and here's the other carbon. That carbon's going to have an oxygen with a minus charge on it, and then it's going to have that R group on it, and then that methoxy group. So we're going to come up here and get an R group, and then we have an O, right, CH3 there. That's your OCH3, right? Okay, so at that point in time, we're getting closer. This is like a tetrahedral intermediate. So we're going to come over here, and we're going to kick off methoxide. All right, so what that's going to give us here is our oxygen, carbonyl, R group, carbonyl, R group. And we're really just about done. There's only one thing to point out here. As we go through and look at our reaction conditions, we're using methoxide. Methoxide has a pK of about 16, but you've made a carbon atom with this dicarbonyl that has a pKa of about 11 or so. So we see a deprotonation there. So what happens is that one of the H's, or the H, from this position is going to be deprotonated. So CH3O minus. We'll come around and grab that H to do this. In the end, it doesn't have a huge impact on what the product is, but it's just something that we have to consider. So we go through here and kind of redrawing that. So here is your R group right now. That's your minus charge. It'll be right there. And then coming over here, you have your other carbonyl. That's this position. And then you have an R group right here. So we just redrawn that also as we've gone through and done this. And then what you do is you do an acid workup. So the last step that you do, a separate step here, is you do a workup. You add H3O plus here. Right, that's your acid workup. So H3O plus, a dilute H3O plus here, is going to end up giving us our protonated form here. So let's take care of that in a second. So because this is planar right now, you end up getting that as a wedge or a dash. So you get two products there. Let's take a look at crossed Claisen condensation. So just like crossed aldol, as long as we're careful in what our choices are for reactants, we can kind of control the explosion of different products that we might form if we're not careful about our starting materials. So let's look at an example down here below. So here we have an example of a carbonyl that has no alpha H's here, and of course just an ester on this side. Right here we have an ester on this side and only one alpha position here. Right, so if we're thinking about what might happen here as far as the reaction is concerned, let's see if we can go through this a little bit. Right, so here we have methoxide coming around and grabbing that H. To do this, that's your CH2 minus that you'd have there. Okay, that CH2 minus then is going to come around here and make a bond with this carbon, and then we're going to do that. Right, so when we do that, that'll give us an O minus over here. That's your oxygen with a minus charge right there. And this part of the molecule right here is this guy here. Right, so that carbon, that CH2 minus, is this position. And it comes over and makes a bond right there. Right? And we'll, of course, it's a chiral center right now, but we're not going to worry about that. And then what happens is these electrons come down here and we kick off methoxide. Right? So that gives us this product. Now that then simply gets deprotonated and then reprotonated here. Okay, so our final product is this. So we'll see in some reactions that we're going to see at the end of this chapter that this is one part of a larger step synthesis. So fairly straightforward and not too dissimilar to just doing an aldol condensation type reaction.